Assalamualaikum and salam sejahtera to all of you. My name Nur Hazwani Naili binti Muhammad Nizam. I am from UTM. Today I would like to present my topic, which is optimization of 14 nanometer horizontal double gate for optimum threshold voltage using L9 Taguchi method. The figure shows the evaluation of a transistor and projection technology of CMOS. The purpose of evaluating transistor is to make possible proper application, specification and design of a transistor. To enhance the performance of semiconductor device, shorten the channel length is one of the methodology. The shorter the channel length, the faster it can switch between its on and off states because the current has less distance to travel through the source and drain regions. Since the industry has been moving down to the 5 nanometer technology node with non-planar device, 14 nanometer is still in research since few researchers are still undertaking this work and yet it is still being used in industry. Double gate design is based on CMOS technology while the technologies employed by GAA and FinFET are different from CMOS technology. The figure shows the completed device of 14 nano of double gate MOSFET. Double gate architecture is one of the potential solutions for furthering the reduction of the channel length. Double gate architecture also can improve the performance of the gate length, thus improve overall performance such as greater in on-off current ratio. Next, the materials used in my design is bilayer graphene, which is proven to be suitable materials to have an adjustable band gap, while high K used in my design is hafnium dioxide. The employment of a high K dielectric material with a gate state to obligate leakage current and to reduce the short channel effect. Metal gate used in my device is tungsten silicide, which have variable work function such as suitable to use for both NMOS and also PMOS. The figure shows the VTH value of my design, which is 0.205918, which is in line with the ITRS 2013 for 14 nano size. The shape and electrical properties of a MOSFET device are sensitive to variations in dopant concentrations, which can be influenced by dose, energy, tilt, and also rotation. Higher gate capacitance can be gotten at a more prominent thickness by utilizing high K dielectric, while the L9 Taguchi approach was used to optimize the process parameter fluctuations towards the threshold voltage value. The table shows the summarization of the process recipe for NMOS, which is first step, deposit the silicon with implant 1.0 times 10 to the power of 14 boron. Next, we implant the VTH adjust with 1.103 times 10 to the power of 13 boron and 20 kilo energy and 10 degrees of tilt angle. Then, we deposit the bilayer graphene with thickness of 0.001 micro. Next, we deposit the high K, which is hafnium dioxide with thickness of 0.002 micro, and deposit the metal gate with a length of 0.014 micro and thickness of 0.003 micro. Then, we implant the source drain with 1.0 times 10 to the power of 17 of arsenic, 2 kilo of energy and 77 degrees of tilt angle. Last but not least, we deposit the aluminium for the metal contact. The figure shows the process parameter and their levels. The symbol shows the process parameter. Symbol A, the process parameter is VTH adjust implant, while symbol B is a VTH tilt angle, symbol C is SD implantation, and symbol D is SD tilt angle. And the level for each parameter, level 1, level 2, and also level 3. The figure below shows the noise factor and their levels. which the noise factor for X is VTH energy and the noise factor for Y is SD energy with two level, which is level 1 and level 2. The table shows the Taguchi L9 orthogonal array for each parameter level for A, B, C and also D. The figure shows the completed device of 14 nano by GFET NMOS, which is the brown is a bilayer graphene and the pink one is a hafnium dioxide, which is high K, and the red one is a metal gate, which is tungsten silicide. Next, the figure shows the measurement of the materials in 14 nano by GFET NMOS, which is the gate length of the tungsten silicide metal gate is a 14 nanometer. The table shows the result for threshold voltage value based on the L9 orthogonal array. And the result shows the OV mean for the experiment is 26.01. Next, the table shows the signal-noise ratio level of process parameter. From the table, it shows symbol C, which is SD implantation parameter, has the highest contribution of variance, which is 55%, followed by symbol D, which is SD triangle, which have 17% of contribution. While for symbol A, it contributes only 16%, and last but not least is a symbol B, which is contribute for 13% only. Next, the table shows the best setting parameter for each process parameter. For symbol A, which is VTH adjust implantation, the best value is 1.23 times 10 to the power of 13, which is under level 3. For process parameter B, which is VTH tip angle, the best value is 12, which is under level 3. And next, process parameter C is SD implantation, which the best value is 0.8 times 10 to the power of 17, which is under level 1. And the last but not least is the process parameter D, which is source drain tip angle. The best value is 79 and the level is under level 3. Next, the table above shows the confirmation results for threshold voltage using L9 orthogonal array of Taguchi method with the best setting process parameter. From the simulation, the mean of the threshold voltage is negative 14.35, which is in range, and the value of NTB, which is nominal the better, also in range, which is 30.53. And the table below shows the simulation results of 14 nanometer by GFET double gate, which is the ITRS prediction is 0.191 and the range is between 12.7%. Before optimization, the result for threshold voltage is 0.205. After we optimize using L9 Taguchi method, the result is 0.191. To summarize, the L9 orthogonal array Taguchi approach is a reliable approach for optimizing the process parameters in the development of a 14 nano N-type double gate MOSFET utilizing bilayer graphene, high K and also metal gate technology to attain the nominal value of the threshold voltage predicted by the International Technology Roadmap Semiconductor 2013. According to this experiment, source drain implantation are the most critical attributes in obtaining an optimal threshold voltage value. Only a small variation in the dopant value will have a significant impact on overall performance of the device. Thank you. That's all from me.